hopefully you can hear me. These are the homework solutions and explanations for Chapter 12 homework. 4 problems were assigned last week. The rest of them are assigned due today, which is February 1st. Okay. So we went through these, but I'll just talk briefly. You had an ideal gas at 20 degrees Celsius. If you double the average kinetic energy, it's going to double the temperature. So kinetic energy and temperature are directly related. But we need to make that into Kelvin. So that's 293 Kelvin. So it doubles to 586, and then I just converted that back to Celsius. If we reduce, this looks like a rooting. It should be reducing thermal energy by 10% when cooling. So we would take this initial temperature, multiply it by 0.9, so that's a 10% reduction. That gets me my new temperature of 264 Kelvin, negative 9 Celsius. In this case, we have a difference in pressure between the inside and outside of the eardrum, that's what that word is supposed to say, of 45,000 pascals. That's all we're looking at as the differential in pressure. So we rearrange this formula. Force is pressure times area. So the area of the eardrum we get by pi r squared. We've got the net force, so we're going to figure out we've got that pressure, so we're going to find the net force, and that's about 2.5 newtons. 15, basically if you've got a 35 psi in your tire and the atmospheric pressure it said was 14.7, that means the overall absolute pressure is 49.7. And what that means is if the temperature increases or decreases, even not too much, it's the absolute pressure that increases and decreases proportionally to that. So that would affect the gauge pressure quite a bit. Number 20. So what we've got here is it was a champagne bottle, I think, and the atmosphere outside was 1, inside it was 6, so that's a differential of 5. Figured that out in pascals. It gave you the diameter of the cork, so I got the area of the cork. So we had the net pressure, the area. We can figure out the force, which is 128 newtons. That seems like a lot, but then this really seems like a lot. 17,000 meters per second. So that's about 1,700 Gs, 1,700 times gravity's acceleration. But that only exists for a very short time as the cork is actually exploding. Oh, this is due on February 1st, so I should probably say that. Okay. Yeah. So in this particular case, then we've got for number 12, tells you how many moles we have, initial temperature, final temperature. We've got this sort of diagram which would be going on. That's actually asking about what's going on in part B. If the volume and the moles stay the same, the pressure should increase with temperature. So first convert the volume that was given, which was 50 cubic centimeters, to cubic meters. Then use the ideal gas law, rearrange to find pressure. That's 9.5 million pascals, or 9,500 kilopascals. So we end up going from this initial pressure to this final pressure. I should probably look at my book a little more as I'm going over these because I'm tending to forget them a little bit. So, okay. Next one's problem 30. So it has a football player inflated in the locker room before the game. The air warms as it's pumped. So it enters the ball at a temperature of 27 Celsius. Ball is inflated at gauge pressure of 13 psi and used to play in 10 degrees Celsius. So once the ball cools, what's the pressure? So Tom Brady's a cheater. I'm just going to say that every year because he is. They definitely know how these things work. So the absolute pressure initially was 27.7 psi. But if you look at the PV equals nRT law, the ideal gas law, and we only have pressure and temperature changing, then pressure 1 over temperature 1 is directly related to pressure 2 over temperature 2. So at the first temperature, 27 Celsius or 300 Kelvin, we have this. The absolute pressure at 10 degrees Celsius is this. Well, that's not going to decrease from the atmosphere. So it actually means that the gauge pressure inside would decrease quite a bit. And that's going to decrease from 13 psi to 11.4 psi. So that's about a 15 to 20% difference in there. For problem 34, it says 0.004 moles of gas, follows the hyperbolic trajectory. It's what kind of process is this? In the chapter, it mentions that the constant temperature isothermal process is hyperbolic. The adiabatic process looks similar, but it ends up being kind of steeper at points. So we'll have to maybe talk about that a little bit. For part B, it's asking you for the temperature. In this case, the initial and the final temperatures. So, I don't know if I did this. Oh, yeah, I did. If it's isothermal, they're the same. So find the temperature at any one spot, and it's going to stay the same. So the next one for that is the final volume. Is that right? Yeah, so the final volume was 300 cubic centimeters. So if your pressure goes down by a factor of 3, your volume is going to go up by a factor of 3 if temperature is the same. Problem 35. We had a picture of a process here, and it's going from right to left. So that is an isobaric process. As the pressure is constant, it's asking about the final temperature. The initial temperature of 900 degrees Celsius undergoes that process. So if your volume ends up 1/3 as much and your pressure is constant, your final temperature should be 1/3 as much. But again, we can't think in Celsius. We've got to end up thinking in Kelvin. That's 1173 Kelvin divided by 3 gets us 391 Kelvin, or 118 Celsius. And then to figure out the number of moles in this, we're just going to use N equals PV over RT, 0.0093 moles. And that can be at either one of these locations as long as you don't mix and match. In other words, pick an initial or a final location, use all the data for that. For problem 36, it's asking how much work is done on the gas for the process shown. So we're shrinking down, so there's positive work done on the gas because it's negative P delta V. So we end up getting plus 40 joules. Had again convert to standard units. P73 is the only problem I assigned that deals with this heat transfer, the rate of heat transfer. Although we did that free response in class, the rate of conduction Q over T, really Q over delta T, I guess, and that ends up being 830 joules per second. So we have the thickness of the plastic, we have the area, we have the conductivity constant, which was given earlier in the book for wood, and then the difference in temperature. Obviously, if you had doubled the change in temperature, your rate of energy flow would double. If you doubled the area, rate of energy flow would double. If you doubled the thickness, rate of energy flow would be half as much. So I hope that helps, and I would look over those. You want to make sure those are corrected by the time we have our test.